volcanic detection equipment that is proposed for the summit of Mount Hood will put geologists as close as they have ever been to the heartbeat of an active volcano.
The U.S. Geological Survey actually designated Mount Hood as a very high-threat volcano a decade ago, but now as our
For years, scientists have monitored the Cascade Range with growing unease, particularly the volcanic giants of Mount Rainier, Mount St. Helens, and Mount Hood. All three stand as behemoths of geological energy, each with a unique history of eruptions, seismic behavior, and geothermal activity. Yet nothing had prepared volcanologists for what satellite scans recently revealed: a network of underground magma tunnels, active and pulsating with heat, silently threading through the depths of the Pacific Northwest and connecting these seemingly separate volcanoes in a subterranean triad of potential disaster. The discovery, first flagged by thermal anomalies captured by orbital infrared sensors, immediately sent shockwaves through the scientific community. Before we start, smash the like and subscribe buttons for more updates. The satellite detection was not a mere suggestion of heat signatures or fragmented chambers. It painted a comprehensive, spine-like structure stretching beneath the Earth's crust, linking the deep magma sources of Rainier to those of St. Helens and continuing on toward Hood. What the imagery depicted was a dynamic tunnel system, appearing almost like veins in a living organism, glowing with temperatures high enough to suggest partially molten rock flowing through them. These were not the dormant scars of past volcanic activity. They were very much alive. The implications of this discovery are both thrilling and deeply unsettling. Volcanic systems are often considered individually, with each volcano treated as its own pressure cooker. The newfound tunnels upend that model entirely. The geological consensus had long assumed that Rainier, St. Helens, and Hood, while part of the same tectonic belt, were largely isolated in their magma plumbing. This new revelation implies that they may instead form a collective system, a superstructure of geothermal energy intimately connected below the surface. One of the immediate realizations is that pressure changes in one of these volcanoes could rapidly influence the others. For instance, should St. Helens, already known for its devastating 1980 eruption, begin to accumulate magma at a faster rate due to deeper mantle activity, that excess energy and molten material could theoretically surge through these tunnels, feeding into Rainier or Hood. A volcanic system no longer acts as a solitary chamber, but as part of a network, a shared artery of magma that shifts and surges with regional consequences. The nature of these tunnels is unlike anything previously documented in the Cascades. While dikes and sills are common features in volcanic geology, cracks filled with molten rock that can lead to eruptions, these tunnels seem to represent more stable conduits, broad enough in some regions to allow for the continuous flow of magma rather than just episodic intrusions. The satellites captured signs of rhythmic thermal pulses, suggesting that these channels are active and dynamic, not just static features of ancient lava movement. Geophysicists immediately began comparing the observed patterns to other known volcanic networks across the globe, particularly in Iceland and parts of Indonesia, where interconnected systems have occasionally demonstrated the ability to trigger multi-volcano events. But nothing on record has indicated this kind of direct connection between major active volcanoes in the continental United States. These satellite findings forced a re-evaluation of decades of research. Instruments were recalibrated, historical eruption data was reanalyzed under this new paradigm, and models began to take shape illustrating how energy transfer might occur across these vast underground highways. One particularly sobering model indicated that a significant eruption at Mount Hood could initiate a domino effect, forcing magma upward toward Rainier through tunnel segments weakened by decades of pressure accumulation. That, in turn, could destabilize the ice-capped peak of Rainier, which holds one of the largest glacial systems in the lower 48 states. An eruption there wouldn't just be a volcanic event, it would trigger catastrophic lahars, volcanic mudflows capable of sweeping through populated river valleys in minutes. The interconnected magma system also sheds new light on tremor patterns that have puzzled seismologists for years. A series of low-frequency earthquakes, often called deep tremor and slip events, have rippled through the Cascadia subduction zone at intervals, yet their cause remains speculative. Now, with knowledge of these tunnels, scientists believe these tremors could correspond to pulses of magma moving through the system, slow, deep, and nearly undetectable until they reach a critical threshold. The existence of these connections adds a chilling layer of meaning to what were once thought to be benign seismic anomalies. Another unexpected detail came from isotopic analysis. Volcanic gases measured from vents at Rainier and Hood have shown periodic shifts in composition, sometimes resembling emissions more typical of St. Helens. These anomalies were previously attributed to local changes in the magma source or contamination from surrounding rock. Now, those explanations seem insufficient. The presence of shared magma pathways means that gas signatures could be mixing, a literal fingerprint of the subterranean connectivity at play. The consequences of these tunnels reach beyond just eruption potential. They influence how magma differentiates and evolves. In a typical volcano, magma sits in a chamber, slowly changing in composition as minerals crystallize out of it. But in a network system, that process is more complex. Magma can migrate, mingling with different pockets, altering its chemistry, viscosity, and explosiveness. This means that even if a volcano appears quiet on the surface, the inflow of new, more volatile magma from a neighboring system could set the stage for a surprise eruption, more violent than any expected from historical precedent alone. These revelations have also reignited concern over the broader tectonic activity of the region. The Cascades sit above the Cascadia subduction zone, a place where the Juan de Fuca plate dives beneath the North American plate. It is one of the most enigmatic and dangerous tectonic boundaries on Earth, capable of producing magnitude 9.0 megathrust earthquakes and tsunamis. The interaction between the subducting plate and the overlying mantle is what fuels the volcanic activity of the Cascades. If that system is more integrated than previously believed, then any major tectonic event could potentially activate multiple volcanoes in succession or simultaneously. Researchers have begun correlating recent swarms of micro-earthquakes under Hood and Rainier with minor increases in gas emissions and ground deformation. While these indicators were once considered unrelated, the framework of interconnected magma tunnels suggests a different picture. These could be symptoms of the same underlying cause, pressure equalizing through the system in response to deeper mantle activity. Like a system of connected syringes, a push in one plunger leads to a rise elsewhere. From a monitoring standpoint, this discovery dramatically alters the calculus. Volcano observatories can no longer afford to focus their attention on individual peaks in isolation. Real-time data now needs to be synthesized across all three mountains, perhaps even beyond, to capture a fuller picture of risk. GPS stations, seismic monitors, gas sensors, and satellite imaging must all be networked and interpreted under the assumption of shared subsurface behavior. This requires a logistical and conceptual overhaul in the way volcanic risk is assessed in the region. There are also implications for geothermal energy exploration and the study of planetary geology. The structure and behavior of these magma tunnels could offer a real-world analog to suspected volcanic systems on other celestial bodies, such as Mars or Jupiter's moon Io, where interconnected magma reservoirs are hypothesized to exist. The data gathered here could help inform future missions and models beyond Earth, adding new depth to our understanding of volcanic processes across the solar system. But in the immediate term, attention remains firmly fixed on the Pacific Northwest. The region's dense population centers, from Seattle to Portland, lie within striking distance of these volcanoes. Any significant increase in volcanic activity could place millions at risk. Emergency preparedness frameworks are being reviewed in light of the discovery, with emphasis on evacuation timing, lahar pathways, and ashfall distribution. Yet the challenge remains in the unpredictability of such a system. Unlike a single volcano where patterns can sometimes be established based on prior behavior, a network system defies easy categorization. One of the more disquieting aspects of this discovery is its silent nature. The magma tunnels have existed undetected for potentially thousands of years. Their activity has gone unnoticed, masked beneath the noise of tectonic shifts, seasonal weather, and normal geological fluctuations. Only the advent of high-resolution satellite thermal scanning, bolstered by machine learning algorithms designed to detect anomalies, revealed their presence. The very fact that such a significant geological structure could remain hidden until now has forced scientists to reconsider what else might lie undetected beneath our feet. Even now, as new data continues to stream in, questions outpace answers. How fast does magma move through these tunnels? Are there pressure valves or natural choke points within the network that could stall or accelerate flow? Could the system be expanding, with new branches forming, or has it remained stable over time, only recently becoming more active due to deeper tectonic pressures? The research teams tasked with monitoring the situation are working around the clock. Some have installed temporary seismic arrays on the flanks of Rainier and Hood. Others are deploying drone-based gas sampling units near volcanic vents. Helicopters fly daily routes, scanning for changes in thermal output, while Deep Earth imaging teams are revising their models with updated gravitational and magnetic field data. What emerges is a picture of a region in flux, not overtly violent, but quietly, restlessly alive. Speculation abounds in the scientific corridors. Some geologists suspect the tunnels may explain periods of volcanic dormancy interrupted by sudden violent eruptions. The magma may have been flowing from one mountain to another during those lulls, recharging systems in ways that were invisible to surface-level measurements. Others suggest the system might serve as a pressure release valve, dispersing magma across a wider region and preventing larger, more catastrophic eruptions at any single peak. Which of these interpretations proves correct may determine the fate of countless lives in the years to come. As more satellites are trained on the region and more sophisticated sensors deployed across the Cascade Range, the full complexity of this underground labyrinth will begin to emerge. For now, the discovery stands as one of the most significant geological revelations of the decade, a reminder of how much we still don't understand about the planet's internal workings, and how thin the crust is between normalcy and eruption. The mountains of the Pacific Northwest have always inspired awe, but now, that awe carries a new weight, shaped by the knowledge that they may be far more united and volatile than anyone ever imagined. The emergence of magma tunnels linking Mount Rainier, Mount St. Helens, and Mount Hood has not only overturned conventional geological models, but has also triggered a massive reassessment of regional volcanism from a systems perspective. With this new understanding, research efforts have expanded rapidly to examine what this interconnectivity might mean for the deep architecture of the Earth beneath the Pacific Northwest. Not just in terms of risk, but in terms of Earth's internal mechanics, and how volcanoes talk to each other over geologic time. One of the most intriguing aspects under investigation is how the discovery could affect interpretations of volcanic dormancy and reactivation. Historically, scientists classified volcanoes as active, dormant, or extinct based on surface observations and eruption history. Yet this binary view is being challenged by the tunnel revelation. If a volcano hasn't erupted for centuries, but remains part of a wider active network of molten conduits, is it truly dormant? Mount Hood, for instance, last erupted over 200 years ago, yet now appears to be directly connected to the more frequently active St. Helens. This places its perceived dormancy in question. It may in fact be experiencing subtle intrusions of magma that have gone unnoticed because they do not result in surface eruptions, activity that could ultimately destabilize the mountain from within over time. Moreover, the nature of heat distribution through the tunnel system is being explored in unprecedented detail. Thermodynamic modeling suggests that the interconnected tunnels don't simply serve as passive pathways. They may actively redistribute thermal energy across vast regions of the lithosphere. This thermal migration could accelerate rock melting in areas previously believed to be too cold for magmatic activity. In practical terms, that means new magma pockets could be forming in locations previously thought geologically insignificant, potentially seeding new vents or fissure systems in the broader Cascade region. This heat redistribution has cascading effects on rock strength, pressure gradients, and chemical diffusion within the crust. The rock surrounding the magma tunnels can undergo transformations, becoming more ductile and less stable over time. It also becomes more susceptible to fracturing during even minor tectonic stress events. This creates conditions ripe for creating new conduits or branching arms of magma flow, further complicating efforts to predict where pressure will localize and how it might manifest in surface activity. Another rapidly developing area of study focuses on the dynamic chemistry of the magma itself, as it flows through these extended networks. Magma is not a uniform substance. Its composition can vary significantly depending on its source and the types of rocks it assimilates during ascent. As it moves through the tunnel system, magma from different sources can mix, forming hybrid compositions that may not match any of the parent volcano's historic eruption profiles. This has profound implications for forecasting the explosivity and style of future eruptions. For example, if silica-rich magma from Rainier were to blend with more basaltic magma from St. Helens, the resulting mixture could generate an intermediate composition that behaves unpredictably. It might erupt more violently than basalt, but less viscously than rhyolite, defying expectations and complicating emergency planning. These mixed magmas could also crystallize at unusual rates, changing eruption timelines and gas content in unpredictable ways. Such volatile interactions between magmas of varying origin further underscore the chaotic potential of a connected volcanic system. The mineralogical evidence of this interconnectivity is beginning to show up in unexpected places. Samples of tephra, volcanic ash deposits, collected from recent minor eruptions and fumaroles at each volcano, are now being reanalyzed with high-resolution mass spectrometry. Already, trace mineralogical signatures typically associated with St. Helens have been found in vents near Rainier, including rare crystal structures and gas inclusions that suggest deep magma mixing. These are the geological fingerprints of the tunnels in action, offering hard evidence that they aren't just structural possibilities, but chemical realities influencing active volcanism in real time. Alongside the geophysical work, researchers are turning to simulations and machine learning models to map future eruption scenarios. Unlike traditional eruption models that simulate a single volcano's activity, these new models must account for the behavior of a networked system where pressure shifts, gas buildup, and fluid dynamics occur across multiple nodes. Some simulations show that a rupture near Hood could result in pressure waves that push magma sideways toward Rainier, even if there are no outward signs of change on the surface. Others indicate that gas trapped along a section of tunnel beneath St. Helens could destabilize a region under Rainier, triggering a chain of reactions difficult to foresee without real-time data synchronization. To better understand this evolving system, teams have started drilling deep boreholes around the volcanoes to install specialized instruments. These include muon detectors, tools capable of imaging density changes deep underground by measuring the flow of cosmic particles through rock. By tracking changes in density around the tunnels, scientists can detect magma movement before seismic instruments might even register a tremor. This emerging field of volcanic tomography is being fast-tracked to provide a clearer picture of what lies beneath and how it moves. At the surface, vegetation and groundwater systems are beginning to reflect subterranean changes. Forest ecologists working in the Rainier Basin have reported unusual die-offs of trees in specific radial patterns, with no evidence of disease or insect damage. Soil temperature readings in these zones have risen slightly over the last 5 years, hinting at subtle geothermal influence rising from below. Some shallow wells have also shown increases in dissolved volcanic gases like sulfur dioxide and carbon dioxide, silent indicators of magma encroaching on hydrological systems. These environmental changes, while seemingly minor in isolation, could act as advanced indicators of system-wide shifts. The magma tunnels could, in effect, function as giant pressurized pipelines that leak heat and gases slowly through weak points in the crust, leading to ecological shifts years before an actual eruption. This reinforces the idea that long-term ecological monitoring, including of flora, fauna, and aquifers, must now be part of standard volcanic risk management. One surprising outgrowth of the discovery has been the revived interest in indigenous oral histories from tribes native to the Pacific Northwest. Stories passed down over generations often describe the mountains as talking to one another, or reacting in concert, an idea dismissed by early geologists as metaphor. But in light of the physical connection between these volcanoes, such narratives take on renewed significance. They may encode observational knowledge of past linked eruptions or geophysical behaviors that science is only now beginning to measure. Linguists and anthropologists are now working alongside volcanologists to examine these stories more closely, parsing them not just for myth, but for embedded data about eruption sequences animal behaviors, and landscape changes. This interdisciplinary collaboration may offer an unexpected key to interpreting the long-term rhythms of the newly uncovered volcanic system. The aerospace sector has also taken notice. Private satellite companies are collaborating with government agencies to increase flyovers of the Cascade Range, outfitting satellites with hyperspectral imaging instruments that can detect even finer shifts in ground temperature, deformation, and gas emissions. These partnerships are enabling a 24/7 watch on a region that could, under the right stress conditions, go from tranquil to turbulent in days or even hours. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on magma tunnels connecting these volcanoes? We want to hear from you. Thank you for watching, and see you next time.